Okay, so we were discussing about the computer architecture. Now, computer architecture consists of two words, computer and the architecture. So when you say computer, it doesn't have to be a laptop or it doesn't have to be a desktop. A computer can be any machine that is doing computing, or in other words, a machine that is processing, storing, and communicating information. Right? In the recorded video, you might have seen there are other computers that are not electronics. So in the broad sense, computers doesn't have to be electronic. However, in our course, we will be limiting our scope to digital electronic computers. Okay. So what are we limiting our course to? Which computers?
Digital electronic.
Yes, digital electronic computers. So after this point, whenever I am mentioning the computer, I will be referring to the digital electronic computers, right? So after this point, I am not going to stress that point. So you can think, anytime I say computer, I am using that particular category. The second word is the architecture. Now, architecture is a process of designing or planning something, right? Usually it is used in the sense of buildings, but it can be used on any scope. So when you say computer architecture, we are talking about designing, understanding, and building computers. So it's a huge topic. We will be only touching the surface of it, but it should be very interesting topic, right? So in this course, we will be focusing about the information processing machines and how we can design and understand their functionality. So how are we going to cover this large topic? As you can understand, a computer is a very complicated machine. So it's not easy to cover even the basics within 8 or 9 lectures. So this is the strategy. First, we will learn about the background. So that included the history that I have already uploaded, and hopefully most of you have seen the video. But other than the history, there are some basic tools you would require to know. For example, have you done electronics in your A-levels? Yes, no, maybe?
Yes.
Yes, you have done electronics, right? Now, we are talking about digital electronic computers. So a fundamental understanding about digital electronics is required. Things like basic gates and logic diagrams and things like that will be required. In addition, there will be some other fundamental knowledge that is required, such as the Boolean algebra and a binary number system. Those are some background information. So we'll start by covering those background information. Once you have the enough background information, we will look at one particular theoretical model. So this theoretical model is known as the Turing machine. It is basically a theoretical description of a computer. Theoretical means it doesn't have any physical implementation. You can't touch it. It just says, okay, this is how it should function. It's more like a mathematical formula. So we look at that Turing machine and we will do some examples, design our own several Turing programs and do it like that. Then we will move into the practical work. Now, a Turing machine says, okay, you have this particular table, it should represent this information. But it doesn't say how that table is implemented. You can say you have a table, but how are you going to build that table? Are you going to use a processor? Are you going to use a compute? Are you going to use a digital gate? Are you going to use a memory? Those things are not described. Therefore, in the later part, we will learn about another design. This is known as the von Neumann architecture. So the von Neumann architecture is a physical way of building a computer. It will give you the guidelines. It's more like a blueprint. It says these are the main components that should be in a computer and how they should interact and work with each other. So that would be one of the core parts in this course. So we will go into different parts of the von Neumann computer and study them, each of them separated, like the processor, the memory, and those things we will look at in details. Then we have a third component, not the third, fourth one. This is newly added. Earlier years, I didn't do it because I felt like there was not enough time, but I thought maybe I should try it. And if we don't have time, maybe we should omit something else. The reason is, up to last year, I have described all the main components and things like that and how they function, but didn't actually design a computer. So yes, you heard me right. This time we are going to design a very simple computer. Hopefully we have enough time to do it. So that means from the scratch, from starting from gates, you will be designing computer, and you may also design your own programming language. Okay, you can call it, we have C and C sharp. Maybe you can call it U or C sharp or something, I don't know. And see how we can make it function and work it. And see, that would give you a pretty good understanding about how the computer works. So it will be basically a design on a paper, but it will be into such details. If you have enough time, you may even actually physically build it using gates, ICs, and things like that. So that would be the key point of this course, to get you the understanding of how the computer works and how you can build your own. But of course, the computer we will be building will be very simple. But the modern computers are much more complicated. They have so many features and so many ways to make them work fast and efficient. So the last topic would be some advanced concepts. So these are some variations of the von Neumann models and some physical ways of improving the performance. So that would be the last thing, such as having multiple cores, how you do parallel processing. Those things will be our last target. Okay. Did you got the idea what we are going to cover in this course? We will have the basics. We will cover the theoretical model. We will look at the von Neumann model and its components. Then we will try to design a simple PC, and then we will cover some of the advanced concepts. Okay. Students, are you there?
Yes, sir.
Yes.
Okay, good. Right. Now let's move to the today's topic. Now in the original one, in the LMS, I think I had this topic a little bit later. The first one I put was, I think, the binary logic or the something else, but I made a slight change. So today we are going to cover about the data representation. So that's why I named as chapter 2, but anyone who had gone a little bit earlier in this course might have recognized this as the chapter 4. But not to worry, these are some basic background information. So there's no particular order. You can cover the data representation earlier or later, it doesn't matter. So this is what we are going to cover today. Right. I shouldn't have shown that slide. So you are humans. So how do you interact with each other? What kind of media are you using? One media is already here, the Zoom. So there we can see and hear each other. So that means we can see the image and the sound. What else?
WhatsApp.
WhatsApp. Okay, you're talking about applications. Okay, right. But if you look at a little bit more wider range, you have the video. Video means in the images and things like that, and you have the audio, and you may also have things like text, like the chat, right? So we use these things, pictures, text, and sounds, and things like that, to interact with each other. Now, can a computer talk to itself or represent things inside using such a process? Now, unfortunately, it can't, right? The computer need to process information, as we have learned in the first recorded session. It's a machine to process information, communicate with each other. So it needs a way to represent information. But you know, computers are using current, and in fact, they will be using voltage to represent information. Right? So we will be looking at different ways to represent information using voltages. Right? For humans, it's easy. I can draw something and show it to you. Or I can speak something, or I can show a gesture. But the computer can't draw something. It might draw it in the monitor, but that's for us to see. Inside it, it doesn't have a drawing pad and a pen. Inside it, you only have electronics. So that means inside it, you only have currents, voltages, resistance, and things like that. So it needs a way to represent information inside the computer, and that usually is done by using voltages. Now, there are two different ways to represent data. One is called analog, other one is called the digital. So the main difference is analog is a range of values. So you can have a set, you can have anything in between. While the discretes have different values, distinct values. Right? Can you give me a everyday example of a continuous range value in a continuous range or an analog value? Can you give me an example?
Temperature.
Sorry, which one?
Temperature variation.
Yes, temperature is a continuous variable. You can have 24, then it will go to 24.1, 24.5. You don't have to skip. It's continuously changing. Anything else? Temperature is a good example. In your everyday life, what kind of things do you measure as a continuous range, and what kind of things do you measure as a discrete range?
Time.
Time, okay. Okay, you can think of it as a continuously flowing. You are thinking in two advanced ways, like you are thinking like scientific answers. If you go to a shop or supermarket, Kiehl's or Cargill's, what kind of things do you buy, and how? Which of them are continuous, which of them are discrete? Or if you look at your home, what things do you see as things that are continuously changing, and what things as discrete? For example, think about your weight. Is it a continuous variable or is it a discrete variable?
Yes, continuous.
Continuous variable.
It's a continuous variable because you don't go from 65 to 68, suddenly jump. You gradually increase or decrease your weight. Anything for a discrete variable? Something you see in everyday?
Height.
Sorry?
Height.
I didn't get your word quite
Height.
clearly.
Height.
Height. Now, height is actually a continuous variable. If I heard correctly, you said the word height. So if you're meaning the height of a person, it will change gradually. You don't just skip one person and suddenly jump to the other level without going through the intermediate. You just grow continuously. You just skip to the other level. For example, we can take the number of students in this particular Zoom session. Now, is it a discrete one or is it a continuous one?
Discrete one.
It's a discrete one. You can have, right now you have 28, so it can go either 29 or you can get to 27. But it will not get 28.5, right? It won't get 1 1/4 students in the Zoom. That's not going to happen because there are prohibited values in that range, prohibited values between them. Right? So that's the main difference. If you have a continuous variable, you have a range like this. So it can take any value between the minimum and the maximum. So similarly, if you are representing voltages, in an analog system, the voltage can be in a range. But if you're going with the discrete variables, you only have fixed points. It can't take some intermediate values. It can't take arbitrary values. You can only take the given fixed set of values. Right? So, but here we will be only focusing on the digital data representations. Okay. So what is the main advantage between the analog data and the digital data? Let's say when compared to analog data, what is the main advantage of digital data representation? Can anyone guess?
Finite values.
Finite values. Okay, that's a little bit of, okay. Can you be more precise? When you say finite values, it can be interpreted in different ways. What do you mean by finite values? So there are two advantages. One advantage is it's easy to design circuits, because you know exactly what kind of values you are going to get, either zeros or ones or something like that. You don't have to worry about intermediate values. But the most important thing is it allows you to reduce the noise. Okay, so let me do a very quick demonstration. Let's say you have a signal source here, and let's say I'm sending this data to someone here. So if you are using a continuous variable, so it can take any value within this range. Let's say the value I'm sending is 2.5 volts. However, when I'm sending this, on the way, it gets some noise added. Right? Let's say 0.1 volt, noise gets added. So the person at this end will get 2.6 volt. Now the person here knows there will be some noise in the transmission path. So it might get something like plus or minus 0.1 volts. So this person can assume, although he get 2.6 volt, the correct value can be in the range of 2.5 volt to 2.7 volts. That's the only thing he can guess. Can you see my drawings clearly? Do I need to zoom my camera? Is it clear?
Yes, sir, it is clear.
Okay. So this person get 2.6 volts. He can only say the value sent by the other person is between 2.5 and 2.7. He can't be very precise because he don't know how much noise is added. It might be 0.05 plus, or it might be minus 0.01. Since this is noise, we have no control. So it can be in this range. Now think of the same scenario, but this time, this person is sending a digital data. Let's say this is a digital data which can represent by either 0 or 5 volts. And this person also knows it. So now I'm sending the data. Let's say 5 volts. Again, 0.1 noise get added. So now this person receives 5.1 volts. But the receiving person knows this is a digital data and it should only have 0 or 5 volts. So he can deduce, since this is very close to the 5, the actual value sent by the other person must be 5 volts. Even if the noise is negative and if he get 4.9 volts, he can again deduce it must be 5 volts. But in analog case, both this 2.5 or 5.1 or 4.9 or all these values are valid values. So he cannot separate the noise and the actual or the valid value sent from here. But in the digital case, you can very easily remove the noise and get only the correct answer. Is it clear for you all?
It is clear, sir.
Okay, so this is important in computers because you don't have only a single component like this. You have thousands of components, right? So if it's an analog circuit, each noise gets added to the step as you move ahead in the process. For example, in the next time when he's sending, this 0.1 noise will be also here, and any other noise will be also included. So if you have a very long process, at the end you will have a combination of lot of noise in that one. So it's a problematic, it will introduce errors. But in the digital one, this person knows it's 5 volts, so next time when he's sending, he had already removed the noise from the previous stage. So there won't be noise, so it will be easy for this person to process it, and we can have a very large computer or very large circuit that works very precisely when compared to an analog circuit. Did you get the idea why we use digital circuits in computers? Okay, I believe you have got the idea. So that's the important thing. So even using imperfect components, we can build a perfect logic circuit to do some perfect maths. Okay, so let's move to today's main topic. So now we know the two types of digital data representation, and we will be only focusing on the discrete type. That means the digital data representation. Right? So when you say discrete, there can be several levels of data representation, but the most common usage is 2 levels. So 2 is meant as binary. So when you say binary data, that automatically represents 2 levels, 2 discrete levels. Those are the only valid levels for the data representation. In the abstract level, we mark them as either true, false, 0, 1, or something like that. But inside the computer, they are represented using 2 different voltage levels, maybe 0 and 5 volts, something like that. Okay, so why do we need to do the conversion? The thing is, the computer inside has only electronic components, therefore everything is represented using binary. Right? But how many of you are good in binary? Can you talk to each other in binary? Do you write a WhatsApp message using binary?
No, we can't.
No, you can't, because humans are not wired to handle binary. We are more used to analog and other images and things like that. So there is a conversion required. Computer can only understand binary, but humans are not good at binary. So you need to do a conversion. So that's the thing that we are going to discuss today. Right? So what kind of thing do we need to convert? Right? We need to convert all the kinds of things. For example, at the moment, you are seeing me. So my image is there, but when it goes through this internet, it is actually converted to binary electronic signals, binary electric pulses. And at the other end, it reassembles and show you the image. Similar for the voice. Right? So there are a lot of things that will be converted, but we can categorize them into several things, especially at the low level or the hardware level. How many of you have done programming in the previous years or in the previous semesters? Any particular language you had learned? Okay, you all
C.
had learned C. Good. Now let's say you are writing a small program. So program is a set of instructions given to a computer. It will follow it, right? So here are some of the possible lines you might write. Very simple ones. 5 plus 3 and the termination of the semicolon, or something like print hello. Right? So if you look carefully, you will see several things inside it. Now 5 and 3 are operands, or they are data. And you have a plus sign. Plus sign is an instruction, or it's an operator. So we are instructing the computer to add these 2 numbers or this data. Similarly, in the next one, we are giving a command to the computer to print. And then we send information, the word hello. Right? So these things need to be converted to binary. Now, we can categorize them like this. So the data information, they can be either facts, or a little bit precise word here would be the data. So the data can be either characters or they can be numbers. And we also have some instructions like do the addition, print this one, send this command, eject the USB disk, Those are commands or instructions. Right? So inside the computer, you have the data and the instructions. So the data can be either characters or numbers. Even a thing like an image is inside the computer represented using numbers. Right? So every pixel is converted to a number. If it's a grayscale, it can be 0 to some other value. If it is a color image, you have 3 lights for RGB in the same way. So inside it's basically mostly numbers and characters, right? So we will be focusing on how to convert characters and numbers into the binary. Okay, did you get the idea? Okay, since some of you feel like sleepy, I will skip the characters for the last one and go directly for the number representation. Okay, so there are different ways to represent numbers. You have the magnitude method, sign and magnitude, ones complement, twos complement, floating point, all these things are there. So we'll start with a very simple one. Maybe the things you have done in the school or maybe in the first semester. Let's say 5. So this is a decimal 5. If you really want to be precise, you can say 10 here. But since we will be using a lot of numbers, I will assume whenever I wrote something like this, you have to think of it as a decimal number. I want to convert it to binary. Can you convert it and type it in the chat window? You already know several ways to convert it to binary. So do it in some way and type it in the chat window. Maybe in the O levels and A levels, I think you have done the binary conversion. Okay, one person answered. Anyone else? Okay. Yes, it's 101. So this method of representing is known as the magnitude presenting. So how do you do it? If you have a very large number, how are you going to do the conversion? Let's say something like 25. If you want to convert it to binary, you start dividing it by 12 and start writing the remainder here. 6, 0, 3, 0. Okay. Did you get the idea? Now we need to write it. Or we'll start with the 5, the simplest example, the one we did. So if you do it, you will get 2, remainder 1, divided by 2, 1, remainder 0. Then you start writing numbers in this order, 1, 0, 1. Similarly, you can write the numbers in this order, 1, 1, 0, 0, 1. So that is the simplest way to convert decimal into a binary. Now, how do you convert a binary into a decimal? Let's say you have something like 1, 0, 1, 1. So this is a binary. Can you convert it to decimal? Put in the chat or you can verbally answer. Let's put another one. Otherwise, the binary and the decimal can get confusing. Okay. So for those who didn't got the idea, to do it, we write it as the below it. You can write the powers of 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4. So this would be 2 to the power 0 is 1, 2, 4, 8, and 60. And 1 into 1 is 1, plus 1 into 2 is 2, plus 0 into 4 is 0, plus 1 into 8 is 8, plus 1 into 16 is 60. So you add them all up, 3, 11, 27. So that's how you convert the binary into decimal. So even in the decimal system, we have the same thing. When you say 535, 132, we are meaning 2 plus 30 plus 500. So the same scenario. Only thing is, instead of having 10 symbols, we have only 2 symbols, 0 and 1. Okay. So you have the basic knowledge on how to do the decimal to binary and binary to decimal. Let's move another step. Can someone convert this into the binary? 2.5. And I will give another question in the similar 0, 1, 1, 0, 0, 1. This is in binary. Can you convert it to decimal? So this is known as the radix point. If it's a decimal number, we call this as the binary decimal point. For a binary number, we call this as the radix point. For those who are confused, I don't think this one is covered in the usual classes. We usually go with the integers, but now we want to represent fractional values. Fractional values are also used in maths and everywhere. So do anyone know how to do this conversion? Convert this binary into decimal? Okay, good. Some people have converted, some people are still a bit confused. Remember, after the reduction point, there's a 0 and a 1. So it's done in the same way. Now for the integer part, use the same thing, 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. What about this part? If you look at a normal decimal number, let's say 56.8, this is 10 to the power 0. This is 10 to the power 1. This is 10 to the power minus 1, or in other words, 0.1. So 0.1 times 8, 6 times 1, 5 times 10. Similarly, this one would be 2 to the power minus 1 and 2 to the power minus 2. So if you write the values, here you have the 1, 2, 4, 8. After the reduction point, you have half and quarter. Now, if you do the similar manner, you will get 0 into 1 is 0, 1 into 2 is 2, 1 into 4 is 4, 0 into 8 is 0, and you put the decimal point. 0 into half is 0, plus 1 into 0.25, 0.25. So you do the addition, you end up with 6.25. Got the idea? Can you convert this particular number, 101.11? So this is binary. I want to convert into decimal. Can you do the conversion quickly and tell me? So this part you can handle. This carries half, this carries 1/4. So half plus 0.5 plus 0.25, 0.75. So here you have 0.75, here you have 5. So you get 5.75. Okay. Are you clear with that one? Is it okay? Good. So in the classroom, usual classroom, I usually go all around the class and find the people who are having problems. But here I can't do it. So I don't know how many of you have finished it and how many of you are still trying to process it. So those people who have typed in the chat window, I know they are either progressing or they have made the mistakes. I can find them. But for those who are not very interactive, please let me know if you are stuck, okay? Because I can't come to individual you and check whether you have done it. In the usual class you can, but in the Zoom you can't. So if you have any problems, immediately ask. Don't wait until the last moment. The reason is this lecture series progress on the one after another. So if you lose some of the basic facts, later lectures will become even more difficult, right? So it's very important to identify anything that you have missed or anything you can't understand and do it quickly and understand, get the concept correctly. Okay. So I believe most of you have done it. So I think we'll,
Sir,
yes.
I have an issue with converting binary number point numbers.
Binary to decimal or decimal to binary?
Yes, binary to decimal.
Okay. What's
Sir,
the...
excuse me, sir. Again, explain decimal to binary point numbers.
Okay, decimal to binary, I think I didn't cover. 2.5 I didn't cover. I will cover it next. But if you have any problem with the binary to decimal, let me explain. First, you get the binary number. Let's say 1010 0.010 something. Like this, you wrote the binary number. This is the redux point. Then after it, you write the powers of 2. So you can say this is 1, 2, 4, 8. Okay. After this, you have the fractional values. You go like half, 1/4, 1/8. In the earlier one, I used 2 to the powers to show it. 2 to the power 0, 2 to the power 1, 2 to the power 3, like that. But these are the actual values you will get. Then you multiply each of them and add them. So here you get 8 plus, this is 0 plus 2 plus 0 into 0 plus 0 into half is 0 plus 1 into 4 is 0.25 and this is again 0. So when you add them up, you get 8, 10, these values add up to 25. So then you get 10.25. Okay, I think now it is clear. If you have any further requirements, please let me know. Now let's look at the other one. 2.5. How do we convert into the binary? Now this whole part, the integer part, you can do, right? So I'm not going to focus about that one. I will be only focusing about the 0.5. You can then append the whole this first binary part to the fractional part and you get the full number. So how do you convert 0.5? In the earlier case, we used to divide the number continuously. But in this case, we are going to multiply it continuously by 2 and we are going to get this whole part, or whether this is 0 or 1. So I multiply it by 2 and I get 1.0. So this is my fractional value. So I can write 1, 0.1. So 1 comes from here. But this is not a very good example because you do it in only single go. Let's say 0.25. You multiply by 2, you get 0.50. So this is my first digit or first bit. Then you multiply it again, you get 0, 1, 0. So this is my second digit. After that, you have 0. There's nothing to multiply. You only get zeros. So you get 0, 1. So 0.25 can be written as 0, 1. Okay, let's try another example. Let's say 0.625. You again multiply by 2. So what is the value? Get 50, 2, 1, 2. You take this digit, this bit as the first one, multiply the remaining. Now remember, when you multiply, you are only multiplying the fractional part. You should not multiply this one and say 2. Okay, you take this as the one of the bits in the answer. Okay? You only multiply the fractional part. So this is not 0. You have to multiply it again. So multiply it again, you get 50. But this time there's no whole value coming. So this is the second bit. You multiply it again, you get 0, 0, 0, 1. So this is the third bit. Now you can see I have reached the 0 in the fractions. So there's no need to multiply it further. So I get 1, 0, 1. So 0.625 is redox point 101. So if you have something like, let's say 3.625, 3 can be converted as 1.11, and 0.65 is, we know, 101. Okay, got the idea? So the integer part, you can do it the usual way. Fractional part, you keep multiplying it by 2 until you get to the 0. And every time you get a whole number, you put a 1 in the bit. Every time you get a 0, you put a 0 here. But remember, you are only multiplying fractional part by 2 every time. Okay, got the idea? Can you do this one? 7.75. And let me know the answer. Okay, I think people have got hang of it. Seven is converted as 1, 1, 1. 7.5, you should get again 1, 1. If you have got that, then you have got the correct answer. I think most of you have done it. 2.25. Okay, 2 is 1, 0. 0.25 is actually 1/4, so you can even directly write 101. Here's something for you to chew on. 3.8. Now let's see how many people will get this one done. 3.8. Okay, somebody had wrote the answer. So this would be a little bit tedious thing to do. Why? 3 is okay. You know how to do 3, but 0.8 is the issue. When you say 0.8, you multiply it by 2, you get 1.6. So that's 1. Multiply 0.6, you get 1.2. Then again you get 0.4. Then again you get 0.8. Again you get 1.6. You can get the idea. So you are basically back to the beginning at this point. You are repeating the same thing again and again and again. So you have a non-terminating number. So you will be end up with something like 0, 1, 1, 0, 0, 1, 1, 1, like that, right? So that means you can't precisely represent this in a decimal, in a binary format. Do you think this is a problem with the binary? It is an issue with the binary, but you can find similar things in the decimal. Can you find something similar in the decimal? Some fractional value, when you try to convert into decimal points, that kept on, yes, that one. If you wrote 10, if you say something like 1/3, if you try to convert into decimal points, you will end up with 0.33333 like that. It will never end. It's the same thing happening here, but only thing is now it's happening in the binary. So at some point you have to finish it and you have to truncate it, right? So that means you will be introducing a little amount of error because you are neglecting some amount of values at the end. Similar thing will happen in the binary. Now a computer can't have infinite length number inside it. It has a finite memory. So after some point, it will have decided, okay, this number of decimal places are enough. Rest I will neglect. So this truncation process introduces an error. So that particular error is known as the truncation error. Okay. In some old calculators, if you divide 1 by 3 and try to multiply by 3, you will get 0.999, not 1. That's based to this particular problem. So far we had covered binary number conversion. In fact, this method is known as the magnitude method. We learn how to convert binary to decimal and decimal to binary, including the fractional values. So it doesn't have to be integers. Now you know how to do the fractional values. And you also learn about the truncation error. Any questions so far? Means we are going to move to the next one. Anything you want to clarify? No? Okay. Let's do a very simple addition. I want to do it in binary, okay? Don't convert it decimal and do the addition and convert back to binary. Can you do this addition? And let me know the answer. Okay. You can double check it if you want. You can convert it to decimal and do the addition and you will see the answer is correct. So addition in the magnitude method actually do work. What about subtraction? Can you do this particular subtraction? Now remember, in the decimal system, if you don't have enough value in the given decimal place, you have to borrow something from the other side, from the left hand side, and do the subtraction. Okay, you know how to do the subtraction as well. Good. How about this one? Can you do the second subtraction? Okay, now this one is a problem. Why? It is clear this, when you try to subtract, the first number is smaller than the second number. So you should be getting a minus value. Okay, somebody had typed minus 100. In a way, you might be correct, but remember, inside the computer, everything has to be binary. Right? So this minus sign is not a binary one. So you can't use the minus sign in front. Okay. So you should get a minus value. Unfortunately, at the current method, we don't know how to represent a minus number. We know how to represent integers. We know how to represent real fractional parts, but we don't know how to represent the negative numbers. So that's where the second representation method comes in. We call it as the sign and magnitude method. So it's basically the same thing as the magnitude method that you have learned so far. Only thing is, at the front, you will be putting a sign. We do it same thing for the decimals. We put a plus sign or minus sign to represent whether it's a positive or a negative. We usually neglect the plus sign because it's so common, but in reality, you should be putting a plus sign if you want to be 100% accurate. But in the binary, you must always put a sign. You can't neglect it as assuming it's a positive number. Okay. So if you want to represent plus 3, we can represent it like this, 0, 1, 1, which is basically what the number means in magnitude methods. If you want to represent positive, we put an extra 0 at the front. This is called the sign bit. If you want to represent the negative number, let's say minus 3, you put a 1 as the sign bit. So for the positive numbers, you put a 0. So for the negative numbers, you put a 1. But the idea, the remaining part is basically the magnitude, which you had already calculated. Shall we do another question, small question? I want you to convert plus 5 using sign and magnitude method, and also minus 5 using sign and magnitude method. Can you quickly do it? What is plus 5 and what is minus 5 in sign and magnitude method? Okay. Okay. So 5 is basically 101. But in the sign and magnitude method, you have to put an extra bit at front to show the sign. So it's a positive number, you put a 0. Similarly, if you want to represent minus 5, 5 is actually 101, and minus 9 is represented by adding a 1. So minus 5 means 1, 1, 0, 1. Now, of course, if you want, you can add leading or trailing zeros to a number, but in sign and magnitude method, you have to be a little bit careful. Let's say you are representing plus 2. Now 2 can be written as 10, or it can be written as 010, or it can be written as 0010. Just like in the decimal number system. If you have 6, you can write just 6, or you can say 06, or you can write 006. the value doesn't change. So if you're using only the magnitude method, these are all valid. And if you're using the sign in magnitude method, you have to add the sign to the front. So you can write this as a sign bit 0, 1, 0, this is correct. Or you can say 0, 0, 1, 0, again this is correct. If you add another 0, this would be correct. So whatever the numbers you are adding to the front without changing the value is known as the leading number, leading trailer. Right? And similarly, sometimes after the redux point or decimal point, you can add zeros at the back. If you are using a -2, the same case, you can say 1, 1, 0, or you can say 1, 0, 1, 0, or you can say 1, 0, 0, 1, 0. All these have the same meaning. This is the sign bit. And all the remaining parts basically represent the number 2. So you can have different number of bits representing the same number. Right? This is important because computers has a way to standardize the size. So if it's an 8-bit registry, you might want to fill the front with zeros or ones. So it will be having the same fixed memory value. Are you okay with that one? Okay. So this is how you do the sign and magnitude method. You can do the opposite as well. If you get something like 1, 1, 0, 1, and if this is a sign and magnitude method kind of thing, how do you convert it? The first bit is the magnitude. Sorry, first bit is the sign bit. So 1 means it's a negative. And 1, 0, 1 means it's a 5. So this is -5. If you got something like 0, 1, 1, this is the sign bit, so it's a positive. 1, 1 means 3, so this is a positive 3. So this is +3. So how do you, this is how you convert it back into the decimal. So by now you should know how to do a decimal to sign and magnitude and sign and magnitude to decimal. Is it okay with you, everyone? Any questions you want to ask?
So I have an issue. I have a question. So basically, it should be mentioned sign and magnitude method. Then only we can
Yes,
take
that's
that first
a
bit.
very important thing. At the beginning, I show you there are different ways to represent numbers, right? It should be mentioned which method you are using. Otherwise, the same binary pattern can be interpreted in different ways, right? If it's a magnitude method, you will get a different number. If it's a sign and magnitude, you get another number. If it's any of the other formats, you will get a completely different number. So basically, it should be mentioned which method you are using, at least in this particular course. Now, there might be other courses which only focus on the positive integers. So they may assume all the things are magnitude method. But in this course, we will be using all the several different methods of representation. Right? So in this particular session, when I say sign and magnitude, it has to be mentioned. When I say if a binary number is there, but it doesn't, let's say magnitude only, then it has to be treated like that. So it should be mentioned what method is used to represent a number. Is it clear now?
It is clear, sir.
Okay. Right. Now we are going to the next type of data representation, which is called ones complement. Now, the sign and magnitude method can represent binary numbers, but it has some issues. For example, you have to be very careful about the sign bit. It doesn't automatically shift according to your calculations. For example, if you try to subtract a smaller number, a larger number from a smaller number, it doesn't automatically change to a negative. Right? So there can be issues like that. And also, there is an issue of the 0. Right? You can say 1, 0, 0, or you can say 0, 0, 0. So that basically says positive 0 and negative 0. So that's again an issue. Right? 0 doesn't have a sign like that, but here you have two different signs assigned for the 0. To overcome that, we use something called the 2's complement. But before going to the 2's complement, it's easy to learn the 1's complement. So that's why we are learning the 1's complement. So the 2's complement is the good way to do the maths. But to do that, first we need the 1's complement. So how do you represent numbers in 1's complement? Now the positive numbers are basically the magnitude method. If you look at the table, you can see all the positive numbers are basically same as how you do the conversion at the first time. It's a magnitude method. So what about the negative numbers? Can you see the similarity between these two? Some pattern between positive number and the negative number?
Yes, they are inverted like other.
Yes, they are inverted or complemented. If it's a negative number, you basically change their bits to the opposite value. Right? You basically toggle the bits, right? So if you have +3, you have 0, 0, 1, 1. If you have -3, you simply flip the bits. So 0, 0 become 1, 1, and 1, 1 become 0, 0. So you get this particular kind for the negative number. Now, let's try to do some exercise on this one. So if you have positive number to be converted to 1's complement, it's easy. You simply follow the conversion rule of the magnitude. If it's a negative number, you do the conversion, but then you do the flipping of the bits. Okay. For the positive number, you just do the magnitude method. For the negative number, you do the magnitude method and then flip each of the bits. But it's important to know there is a number of bits required for each of the decimal numbers. There's a limit that can hold a given number. There's a minimum number of bits required to represent a number. For example, if you look at this carefully, you will notice all the positive numbers have a leading 0. And all the negative numbers have a leading 1. Right? So if you try to add 1 to this one and say +8 is 100, you are misrepresenting the number. Okay. So let's do a small exercise. +3. Can you convert it to 1's complement quickly? And then I want you to do the -3 as well. Now remember, you can add leading zeros for the positive number and you can add leading ones for the negative number. Okay, this can you do it without looking at the table I mentioned earlier? Good. Now +3 can be represented using 0, 1, 1. And if it's 1's complement and you want to get the minus value of this, you simply say 1, 0, 0. Now, can I do this one? Now we know in the magnitude method, +3 can actually be written as 1, 1. This is 1, this is 2, 2 plus 1 is 3. Do you think this is a valid answer in the 1's complement? Do you think this will give you the +3 in the 1's complement? No. Why? Someone can misrepresent, someone can think this as the
0.
0. Yes. So therefore, if it's a positive number, you should have at least one leading 0. Even if you have more, that's fine. If you have more, when you complement it, your negative number will have leading ones. Okay. So in the 1's complement, you can have a number like this. You can add zeros to the front without changing the value. This also signifies this is a positive number. And in the ones complement, you might have a number like this. If you want to change the number of bits without changing its value, you need to add ones to the front. These should be the leading ones. Did you get it? For a positive number, you can add leading zeros. For a negative number, you can add leading ones. Basically, you will simply duplicate in the first bit. If you have ones, you can add ones. If you have zero, you can add zeros. Did you get the idea? Is it clear? Because sometimes students get confused whether to add zeros or whether to add ones to the front. Now it's a positive number, you can add zeros. If it's a negative number, you can add one. But if you add ones to the positive number, then you will be changing the value. So that's incorrect. So you should add only the correct type of bits to the front. Okay, can you convert this into decimal? So assume this is in the ones complement. Can you convert this into decimal? This is not the magnitude method. This is ones complement written. Okay, I can see there's small confusion between people. Okay, first tell me, is this a positive number or is this a negative number? You should be able to decide it just by looking at the number. It's a negative number because you have a leading one. So if it's a negative number, you can put a negative sign and then invert the bits to get its magnitude. So we invert the bits, 1 becomes 0, 0, 1, 0. And this becomes 2. Now don't get confused this with the sign and magnitude method. In the sign and magnitude method, this whole thing was directly interpreted as the magnitude value. But in the ones complement, if it is a negative number, you would have to flip it to get the value. So 1, 1, 0, 1, flip, you get 0, 0, 1, 0, which is minus 2. But if I said 0, 1, 0 in ones complement, then what should I get? Then this is a positive number. I know this is positive number. Since it's a positive number, I don't need to flip these bits. So they will be as it is. 1, 0, 1 means 5. Okay, are you okay with it? So don't mix those different methods. In the magnitude method, every bit is counted as a value for the magnitude. In the sign and magnitude method, first bit is removed as a sign bit and the remaining part is directly interpreted as the magnitude. In the ones complement, first bit can be used to detect whether it's a positive or a negative. If it's a positive number, then you directly convert it as the magnitude method. If it's a negative number, you flip all the bits and find the magnitude of that number. Okay. Shall we try another one? Okay, what are the values for these two? Can you quickly do the calculation? Okay, first one is positive 11. Second one here you have two steps. It's a negative number. You put the negative sign, then you flip it. Flip all the bits, and then you start calculating the values. This is positive, and this part then I can directly interpret as magnitude 1, 2, 8, 11. This is negative, so that means I need to flip all the bits 0, 1, 0, 0, 1. This is negative something, minus 9. Okay, so that with that we complement, we finish the ones complement method. I think everyone got the idea. Now let's move to the twos complement. So this is the most useful method for representing numbers. In ones complement, we had one issue, that is even in the ones complement, you have the positive 0 and the negative 0. If you look at the first row, 0, 0, 0 represent positive 0, and 1, 1, 1, 1 again represent the negative 0. So once twos complement overcome this by shifting the values by 1. In twos complement, this is overcome by shifting the values. Let me share the lecture note. So if you look at the note, you can see this is the table. So the positive part is same. So for the most of the conversion methods, positive part remains the same. So this is same as the magnitude method, the sign in magnitude method, the ones complement, everything have this type of positive part. It's the negative part that will get changed from method to method. So for the negative number, earlier in the ones complement, this was mapped to 0. But here we had shifted everything by 1. So this is called now as a minus 1. Which used to be minus 1, now is called minus 2, minus 3. So everything is shifted by 1. So that is the only difference between ones complement and twos complement. In the twos complement, negative numbers are shifted by 1. Now let's see how we can do that in a calculation. So if it's a positive number, you simply take the ones complement. So there's no change, you can already do it. If it's a negative number, there are two different ways to do it. Either you can add a positive 1 and do the ones complement, or you can do the ones complement and then add 1. Both methods will give you the same result. Okay. Only difference is if it's a negative number, you add the 1 either before doing the conversion or after doing the conversion. For example, here we want to take the minus 4, the twos complement. So the first step is, this is again possible. In this case, we took the ones complement of the minus 4 and then add 1 and you get the result. But if you do it the other way around, Okay, so this is the ones complement method. So let's say you decided to add 1 first and then take the ones complement. That again will give you the same result. For example, when you want to convert -4, you add 1, then it becomes -3, and you take the ones complement of the -3. And if you look at the ones complement of the -3, it's 1 1 0 0. It is same as this one, right? So you have two ways of doing it. You can add the one either before doing the conversion or after doing the conversion with ones complement, right? Shall we do a question on that one? Let's say -6. Can you convert it to 2's complement? First check whether it's a positive or a negative number. If it's a positive number, you are in luck. You just do the conversion like magnetic method or ones complement or whatever method you prefer. But if it's a negative number, you have to be careful. It depends on the method of conversion. So here it's 2's complement. And we can see it's a negative number. So if it's a negative number, we can add 1 here. So it becomes -5. And we take the ones complement of -5. So how do you take the ones complement of -5? We take +5 and flip the bits. So +5 means 1 0 1. But remember, since in the ones complement, if it's a positive number, you need to have at least one leading 0. You can have multiple, but 1 is sufficient. If you want more, you can add them. So this is +5. So the -5 in ones complement is 1 0 1 0. So my answer is 1 0 1 0. If you remember this step, this is the number. We add 1 to the number. Then we took the ones complement of that number. So ones complement of -5 is 1 0 1 0. So my answer is 1 0 1 0. -11. Can you convert into 2's complement? So minus 11, first we need to add 1 to this minus 11, so it becomes minus 10. Now what is the 1's complement of minus 10? We have to have 2's complement of minus 11. This is same as 1's complement of minus 11 plus 1, which is 1's complement of minus 10. So 1's complement of minus 10 is after flipping the bits of plus 10. Now plus 10 can be written as 8, 4, 2, 0. But remember, this is not sufficient. In the 1's complement, when you are writing the number, you need to have at least, if you are taking the positive number, you need to have at least 1 0. If you are taking the negative number, you need to have at least 1 leading 1. So now I am taking the plus 10 and then hoping to flip it back into minus 10. So the plus 10, you need to have at least 1 leading 0. And then I can flip it to 0, 1 0, 1 0. So this is the answer. Okay, are you clear with that one? I see some confusion among the people. Okay, minus 4. I need to do it in sign and magnitude method. 1's complement and 2's complement. Can you do it in all the three? Minus 4, sign and magnitude method, 1's complement and the 2's complement. So the sign and magnitude method, this is the sign, it should be 1, and magnitude is 4. So 4 can be written as 1, 0, 0. Even if you wrote something like 1, 0, 0, 1, 0, 0, that's okay. These will be considered as the leading bits. This should be considered as the sign bit. Now, if it's 1's complement, you have to take the positive 4 and flip it. Now, positive 4, you write it as 1, 0, 0. But remember, you need to have at least 1 leading 0. If you want, you can have more. So minus 4 means flipping of these bits. So it should be 1, 1, 0, 1. Again, you can have some leading ones if you wish, but this part should be there. Similarly, in this one, you need to have these bits and these bits in this one. In between, you can have leading ones. In here, the leading ones are at the front. Now, in the 2's complement, you simply add 1 to this. So you want to take the 1's complement of minus 3. Or since you already have the 1's complement value here, we can simply add a 1 and get the result. If you add 1 to here, you will get 0, 0, 1, 1. Again, if you need, you can add leading ones to this one, since it's a negative number. If it's a positive 4, what's going to happen? Positive 4 in the sign and magnitude method is 1, 0, 1, 0, 0. And in this one also 0, 1, 0, 0. And this one also 0, 1, 0, 0. If you need, you can add more zeros to the front. Is it clear to you? How about others? Is it clear to you? Do you need to do more exercise, or are you okay with this one?
Can you give us another example?
Okay. Then we'll do it step by step. So the most complicated one is the 2's complement. So let's try to do it. Positive doesn't need to add 1, right? Yes, adding 1 is only for the negative numbers. Positive 1, you don't do anything. Positive 1 is almost the same for all the things. It's only for the negatives that you have the issue. Okay. So let's say convert, give me a number, minus 10. No, 10 is wrong. Minus 9 to 2's complement. So what should be the first step? You should detect the sign. Is it positive or negative? Is it positive or negative? The minus 9?
It's negative.
Negative. Right. If it somehow happen to be positive, then it's easy. You just directly go and do the 1's complement or magnitude method or sign magnitude method, whatever you like. So you can go to the magnitude method, but remember you should have a leading 0 if it's a positive number. If it's a positive number, you should have a leading 0. Other than that, you simply do the normal conversion you had learned at school. Okay. So positive numbers are easy. Positive number method, I think it's okay, right? What about if it's a negative number? If it's a negative number, what's the next step? You need to add 1 to this one. Okay. Add positive 1. So it results in minus 8. Then we take the third step, 1's complement of minus 8. And that's the result. So doing this was covered in the little bit earlier. So 1's complement of -8, how do you do that one? Now if it's a 1's complement number, if it's a positive number, nothing to do. You simply put a 0 and put the magnitude method. If it's a negative number, what should you do in the 1's complement? You take the positive, you take the normal magnitude method and flip the values. So if you want to take the -8, I have to take the +8 value, +8 binary pattern, and flip it to get the -8. So I know the -8, actually the flip of the +8. So +8, so +8 I can write 0, 8, 4, 2, 1, like this. Now again, remember, if you are writing a positive number, you should have a leading 0. If you are writing a negative number, you should have a 1. So right now I am trying to get the positive 8 number and after that flipping it. So at the moment I am converting +8 into the binary pattern. So it should have a leading 0. You have 0, 1, 0, 0. Oh, 0 and 0. Then you do the flipping. Once you do the flipping, you end up 1, 0, 1, 1, 1. So -8 in 1's complement is 1, 0, 1, 1, 1. So here we want to get the 1's complement of -8, and we have done that one. So that value is, you can write here, 1, 0, 1, 1, 1. Okay. So the easiest way to remember is we start with sign and magnitude. For the positive numbers, we should have a leading 0. For the negative numbers, we should have a leading 1. So sign and magnitude, it should be easy. And for the 1's complement, for the positive numbers, same as this one. For the negative numbers, you take the positive value and then do a flipping. So once you did that one, you get the number. For the 2's complement, positive number, the same thing. For the negative number, you add 1 and get 1's complement. 1 and get 1's complement. So you can see in the 2's complement, if it's a negative number, you can break it into several steps. You add 1 and take 1's complement. And in the 1's complement, if you have a negative number, you take the sign and magnitude method or the normal magnitude method with a leading 0 and do the flipping. So to do this one, you actually calculate the 1's complement, and to calculate the 1's complement negative numbers, you actually do the magnitude method with the leading 0 and flip it. So that's how all the three are connected with each other. Okay. In the note, I think you have several more examples, so you can check it. Let's move to the last topic, because we have 2 more topics to cover in about 15 minutes. So this is all good as long as you want to write small numbers. But what will happen if you want to write a very large number? Let's say the speed of light. Now in decimal numbers, how are we going to do that? What's the speed of light? You're doing physics, so what's the speed of light? Rough estimate? Okay, that's not a rough estimate. Someone typed, I think someone Googled and typed it. Let's say 3 to the power?
3 to the power 10 of 8.
10 to the power 8. So you can see I'm writing a very large number using this method. What is Avogadro's number?
$23.
Right? So if I want to write this one in the normal method, I would have 0, 2, 1, 2, 3, 4 like that. Write 23 zeros. So that's not efficient. That's not going to work. Right? So we use 10 to the powers to write either very small numbers or very large numbers. We can do the same for the binary numbers. We can have a binary number like this and write it as a power of 2. Right? So here we write it as power of 10, but in the binary we write it as power of 2. So 2 to the power 6 means 1, 2, 3, 4, 5, 6, like that. So this method is known as the floating point notation. So advantage is this allow you to write very small numbers and very large numbers using a small number of bits. You can see I'm using only very small number of bits, but I can write or represent a very large number. So there are different ways of doing the floating point notations. So I'm going to very briefly mention about the IEEE notation. So this is one of the standard methods used in computers. So it's known as the scientific notation, IEEE. So here, now this is different to all the things that you have learned so far, okay? So don't confuse them with them. So for them, for this method, you are actually using a sign bit. The first bit is actually a sign bit, positive or negative. Then you have the biased exponent. That means how many 2 to the powers you have. 2 to the power 1, 2 to the power 3, or something like that. So the next 8 bit represent 2 to the power number. And the last bit represent the mantissa, or the base of the number, 6.022 or something like that. Right? So in the note, you have an example of how it was implemented. And I think I added a link so you can see if you want to try it by yourself. So I'm not going to cover everything, but this is the very brief detail. First, if the number is a negative, sign bit is 1, otherwise it's 0. It's just like in the previous case. Convert the number to binary, treating it as an unsigned number, right? So since you remove the sign bit to the first one, the remaining part you can consider as unsigned. With the sign you have already considered. Normalize the binary point, that means the redox point, must be directly after the first appearance of 1. Now, even in scientific writing, we don't put decimal point at any place we like. We usually write a 1 integer and then put the decimal point, and after that you write the fractional part. So the same format here. Bias the exponent, add 127 to the exponent, store the bias exponent and mantissa without the leading one. Okay. Here's how they had done it. Here's an example. It's a positive number. We are going to convert this one, 172.625. It's a positive number, so sign bit is 0. We put a 0 here. And then we convert 172.627 into binary. So this is its binary format. You know how to do this conversion, right? So you can do it. Then we convert into this standard pattern. Remember, here the redox point is here. But in the standard notation, we have to move it 1, 2, 3, 4, 5, 6, 7 times to the front. So write it like this, 1.011 into the power of 2 to the power of 7. Right? So this is the mantissa and this is the exponent. 7 is the exponent. Okay, now we have done that one. But remember, in the mantissa, you have 23 bits. But our mantissa doesn't have 23 bits. So what we can do is, we can add bits to fill it. We can add bits to fill it. Now remember, this part is actually a fractional part. So when you add in bits, you should add it to the end. Can you remember, in the decimal numbers, it's the same as 6.5 and 6.5000. For the whole part, if you're adding numbers, you should be at the front. 5, 0, 5 or 0, 0, 5. But for a fractional part, when you are adding bits or numbers, you should add it to the end. You will be adding zeros here. So you will end up with something like this. 1.100. And after this binary point, decimal points, you have so many zeros to match the 23 bits. Okay, you have the 23 bits. Then you store the mantissa part. Store that in here. And you take the exponent and you do a small biasing. Biasing means you are adding a constant because you should be able to add both positive exponents and negative exponents. So they are basically shifting the 0th point. So 0, when you are storing in the IEEE format, you will be storing as 127. 1 will be stored as 128. 10 will be stored as 137. And if you want to add -1, you will be storing 126. So you are basically shifting the point. So that's what they are doing. That gets to 134. And you store that as here. So mantissa part is okay. For the biased exponent, you have the 7. Just remember you are adding 127 to the 7 or whatever the exponent and convert it to binary and storing it here. So the final result is something like this. So that's how you do the IEEE conversion. You have a website here, and if you go through the document, you will find some more details. Right. Now I need to move to the character representation. So that will be a very fast and easy session. Before going there, do you have any questions regarding the number conversion? Anything at all?
So they could come first. Like,
Hello?
hello, can you hear me?
Yeah, can you speak a little bit louder?
Hello. Hello.
I still can't hear you quite well. Okay, maybe you can ask a little bit later after checking the mic. Right, so we are going to look at the text representation. Although we say text, it's actually character representation because text is made of number of characters. Characters means letters. Letters plus some of the characters that cannot be printed, like new lines and punctuation marks, things like that, right? So character representation can be done quite easily. What you do is you take a letter and say, okay, this letter is represented by this given pattern. So that's straightforward. Okay. So you can say, okay, this is letter A. This is represented by 0, 1, let's say 0, 0, 0, 1. And letter B is represented by 0, 0, 1, 0. Letter C is represented by 0, 0, 1, 1. D is by other pattern. Like that, you simply do a mapping. Now, don't confuse these with binary numbers. Okay. Now, the computer knows whether it knows it is a number or a character. So, if it's a character, he will automatically convert it to here. If it's a number, then you can treat it as a number, right? So, we are doing a simple mapping like this. So, whenever we type letter A inside the computer, it is represented by this particular way. But the issue is, let's say you have your computer here. You type your document, save it to a USB drive, and bring it to your friends. Now, friend open the document. Now, let's say the friend's computer has a different way. He thinks this is letter Z, this is letter Y, and this is letter X, and this is letter P or something. So now what's going to happen is whatever thing you have typed here, convert to binary pattern, and that binary pattern, when opened in a different computer, converted to different pattern. So whatever the document or the assignment you typed is now cannot be read by the other person because the text and characters are mixed up. Okay. So how do we avoid this one? To avoid this one, we must have a standard. Right? So everyone should agree letter A is represented by some pattern. So whoever typed that letter A produce the same pattern, so anyone else can know it is the letter A. So that is known as the standard. So there are two standards that are familiar. First one is known as the ASCII standard. How many of you have heard about the ASCII codes? You have heard of ASCII, right? So it stands for American Standard Code for Information Interchange, right? And the latest one is known as the Unicode, right? So these are the ones that are used to, two common ways to use text representation. Okay. Now the ASCII use 8 bits. ASCII use 8 bits. Now, how many different patterns can you generate from 8 bits? Can you do a quick calculation and let me know? Now, if you have a single bit, that could be either 0 or 1. 0 or 1. So 1 bit, you can have 2 patterns. If you have 2 bits, you can have 0, 0, 0, 1, 1, 0, or 1, 1. That would basically means 4. If you have another bit, you can have 8 patterns. 0, 0, 0, 0, 0, 1, 0, 1, 0. Right? So if you have n number of bits, you can see for a 1 bit, you have 2 patterns. For the 2 bit, you have 4 patterns. For the 3 bit, you have 8 patterns. In other words, for n number of bits, you have 2 to the power n number of patterns. So for the 8 bit, you can have 2 to the power 6 number of patterns. So in other words, 256 patterns. Right? Here someone saying 2 to the power 7, it should be 2 to the power 8. There was an ASCII standard with 7-bit, but it was changed a little bit several years later into 8-bit standard pattern. Right? So now you have 256 characters represented using ASCII. Now, do you think that is sufficient? Is it enough to have 256 different symbols to represent characters? Is it sufficient, or do we need more characters? How many letters are in the Sinhala? Okay, 60. If you drop that to words that are noticed, could be 58, something like that. Anyway, so you have a lot of characters, and remember you have to use vowels as well. And if you look at something like Chinese alphabet or Japanese alphabet, you will notice 256 is not going to cut it. It's not enough. So that's why later on this standard was extended. So 8-bit was sufficient for the Americans because they were the first to invent the computer, and for the English, 256 was more than enough. You have 126 letters, so that's enough. Even with capitals, symbols, and digits and everything, that's fine. But as the other countries joined this computer community and wanted an international standard for all their text and languages, ASCII became too old. So that's where, so this is the ASCII code. You can see some of the characters represented here. So that's why we have the Unicode. The Unicode allows you to store more characters than the ASCII. Now there are again several Unicode standards, but for example, let's say UTF-16 that use 16 bits. So that addition of 8 bits make it hugely large. 2 to the power 16 is a very large number. So you can store all those things in the Unicode. So you can have English characters, Sinhala and Tamil and Chinese and everything, right? But as Sri Lankans, we had a special issue with the Unicode. So how many of you know how to type in Sinhala? How many of you had typed in Sinhala in some time in their life? Yes, no, maybe, haven't tried it. Nobody had tried in Sinhala? Okay, maybe you are trying the Singlish method, typing Sinhala words in English. But those who had typed will know that there are several keyboard layouts. They call it keyboard, but actually font types, like Vijayasekara layout and things like that. Even nowadays, you will find certain documents, you type it with your own computer or someone else's computer, you take it to other person, and when you open it, the fonts have changed. There are some mistakes, some fonts are different, some text are different, things had gone a little bit astray, right? That is because before the Unicode was invented, Sri Lankans wanted to develop their own standard. Although they say Sri Lankan wanted standard, what mostly happened is several people individually developed their own fonts. So they map their own patterns into the fonts. So when 2 different fonts get changed, it's not only the shape that got changed, the actual characters got changed. When you say letter letter R, you might get letter R or E or something, right? So this continued. So that individual layouts did not match with the Unicode or with each other. So even now you might find some documents. You open with the standard MS Word font, like Esqualibot or something, then the Vijayasekara layout will give you some completely gibberish thing. The reason is the binary representation of letters in those 2 computers or those 2 fonts are different. So that's what happened in the Sinhala case, but now we have a Sinhala Unicode. So most of the fonts are now aligned with Sinhala Unicode, aligned with the Unicode. So between the Unicode fonts, there's no issue. You only change the shape, like whether it's bolded, rounded, how it is written. Only the appearance will change. The actual font, the text or the content will remain the same. But if you try to open it with some other old kind of font, things might get changed, right? So that's the special case about what happened to the Sinhala fonts. So I think with that we come to the conclusion of our one, because number representation we covered early. So is there any other questions you want to ask from character representation? Okay, there's one question. How do you submit the question 1? Question 1, I think I decided to answer it on the text box itself, so you can just type the answer. I think someone did try something about 6-bit computer or something, but you may want to check it again, because now you have more than 6 qubits in quantum computers. Anything else you want to discuss from today's session? What happened to all the students? You seem to be very quiet. Did you got what I covered today?
Yes, sir, we got that.
Okay, a very quick recap. Today we covered about data representation. That means how to convert characters and numbers into binary. Instruction conversion we'll do a little bit later. We learn 2 types of signals, analog and digital, and their difference and the advantage of digital signals. We learn what's the binary data and why it is important to do the conversion. We learn about ASCII and Unicode, and why ASCII is not sufficient, and why Sinhala had a little issue with Unicode fonts. We learn about different way to do the number conversion, magnitude, sign and magnitude, ones complement, twos complement, and you should be able to do all those four methods, binary to decimal and decimal to binary, including floating points, that means fractional parts, including fractional parts and negative numbers. For the last one, or the floating point one, IEEE, I do not expect you to do that calculation by yourself. I put it there just to show how the computers represent the numbers. So the ones complement and twos complement were used long time ago, and the modern day ones use floating point numbers. So those were the things we covered today. So I will try to upload few more videos as we go on. By the way, do you like to join one of the recordings? So I can conduct a Zoom session for the recording, or I can conduct it by myself and upload it to the LMS. Now we will have our Sunday lectures that will be there. I'm talking about some in addition. Do you like to have some additional lectures? Because I will have to record some of the lectures, because we don't have enough time to cover all the topics only by going through the Zoom sessions. So when I'm doing recording, there are two ways to do it. Either I can do it myself, so you will not be there, or either you can ask you to come to that recording session. So instead of recording using the one that you see earlier, I will do something like this particular lecture, but at the same time I will record it and upload into the LMS. So that can serve as to the other people as the video. Okay, I will upload the PowerPoint. It was there a little bit early, but I wanted to change the flow, so I removed some of the content from the LMS so I can upload it, and I will try to upload this video as well. So if I'm to do a lecture or recording with you, when will you be usually free? Do you have lectures or something on Saturday or something like that?
So we have one module,
You have?
one subject.
We have one lecture in Saturday, 4 p.m. to 6 p.m. That's also
That's evening.
Yes, sir. 4 to 6.
Okay, how about Saturday morning, early in the morning, around 7? Okay. Then I will try to, for this week, I will try to record it by myself and upload it. And maybe when you have free time, you can discuss among yourself and see if it suits you, if there's a slot, if you can join the recording session. Otherwise, I will record it and upload as usual into the LMS. So you can view the video and it will be in detail. Only thing is then you won't be able to ask question during that particular session. Only after that session is finished on the next week, you will be able to ask the questions. Okay, now I think it's 11:20. You have something, okay. It's 11:20. Do you have any other questions regarding anything?
So what about the assignments?
Exams, that can depend slightly. Usually we had written exams up to last year. We had written exam where students will come and sit and do the exam. This time I think now we can do it again. Last semester we had some issues because universities were closed. We had to take home assignments and things like that. But I think this time we will be able to do the final exam in the written mode. So you will be asked to come for the exam, and you can find the past papers in the LMS. So it will be in the same format. In addition, you might get some several small take-home kind of assignments, like design this particular circuit, do this one. So they will carry a small amount of marks for this one, for the final exam, but main component will be the final exam. So the format will be the same as the previous years. Anything else? Okay, so
what kind of practical we have in this subject?
that's a good question. Formally, you don't have any practical. This is supposed to be a lecture course, but what we are doing is there would be some digital electronic components, digital electronic circuit designing. So for that, I know you have a separate lab for digital electronics. So some of the lab content will be similar to the ones we have been learning. It's not one-to-one mapping because it's a separate course. My one is a separate one. But you will get some idea of certain digital circuits when you are doing the practical. In addition, there are no dedicated practicals, but time to time we do certain simulations. We use Logisim and other softwares to do simulations. So you may be asked to use those software to either write a small code or to design a small circuit and things like that. Other than that, there are no formal practicals for this course. But if you're interested in doing something by yourself, you are always welcome.
Thank you very much, sir.
Okay, then shall I end this particular lecture and finish off the Zoom session if you don't have any questions? Okay. I think my contact information is on the LMS. So if you find anything that you need to ask or anything clarification, please be kind enough to mail me, or you can ask it in the next lecture. Okay, that's it for today. Thank you. I'll be signing off you now.